Thank you very much for the introduction and very much for the opportunity to talk here. I was going to start with a bio. You probably got that already, but just to fully introduce myself, I did my PhD in astronomy at UCLA. I worked for 20 years at the Lawrence Livermore National Lab, and we were just trading precision optics stories about, oh, I can measure to 100 picometers. Well, I can measure to 10 picometers, which is what happens when laser people are together. I was on the faculty at Stanford for 10 years in the physics department and the Kavli Institute for Astrophysics, and I've been director of University of California Observatory for 3 years. And there's a picture of me at the Gemini telescope in Chile. I actually thought I would just say a little about UC observatories, because that's my day job, so to speak. So as the introduction said, we operate or take roles in 3 facilities. I'm sure all of you are familiar with Lick Observatory, and I would invite everybody to come up there, volunteer for us, sign up for our tours, VIP or otherwise. I've spent, even back to my PhD, I stopped counting when I spent 200 nights at Lick. And the fact that I'm now in charge of it is kind of cool. Our flagship is the Keck Observatory in Hawaii, the twin Keck telescopes that we share with Caltech. And then we're part of the process of building the 30-meter telescope. And there's the Lick picture. Best observatory in the world in the 1890s. No longer true, but still a fairly amazing place for things like technology development, where the first adaptive optics was made to work, for public programs, a lot of which are helped by probably people in this room who come up and help our visitors look through telescopes, and for education. And I actually wanted to show off one of my favorite education programs right now. In collaboration with the Gordon and Betty Moore Foundation, we're running a program to partner with community colleges and Cal State campuses. Lick is officially part of University of California. That's who has core access to it. And it's still important to us, but for people at a community college, being up there and being able to use our research quality telescopes is a pretty amazing experience. You could either be doing a physics lab where you prove Ohm's law, or you could go use our telescopes to show dark matter exists. And in terms of inspiring people to be a scientist, the latter might be a little bit better. Keck Observatory in Hawaii, the 2 world's largest telescopes, originally built jointly by University of California and Caltech. University of California figured out how to break the barriers of conventional glass mirrors and build large segmented active smart telescopes. Caltech figured out how to raise large buckets of money, so it was kind of a natural partnership to bring the 2 of them together. And then the 30-meter telescope, which I can talk about at the end, as people are aware, is in a more complicated position in its development right now, is proposed for construction in either Hawaii or potentially in the Canary Islands, depending on funding in the complicated landscape that we live in right now. Okay, but let me talk about the science. So I like this quote, about 1,000 years old. I'm going to go back even further and then zoom forward into the present and finish in the future, because the question of other worlds is something people have been grappling with kind of as long as we had the concept of there being a world. When Albertus Magnus was writing this, we didn't know what planets were. We knew there were little dots. We knew they moved across the sky in a way that was different than the stars. But other than that, they're just dots. And so when he asked the question, he was asking, were there even other planets? In the sense of large spherical bodies thousands of miles across, did they exist or not? That question was answered not too long after it by Kepler, Tycho, Copernicus, and Galileo, who I'll talk about in a moment. But the modern version of that question, and then the next version of that question was, all right, there's planets in our solar system. Are there planets around other stars? That took longer to answer, but now we know thousands of those. But we still don't know the answer to the question of whether there's a world in the sense of a planet that you can stand on, that has a thin atmosphere, that has water and has life on it. Whether planets like Earth are rare in the universe or incredibly common remains unanswered for now. We're about 15 years, technologically speaking, from being able to answer that question. And that's what I hope I will finish with. So going back another 1,000 years or so to the sort of ancient Greek view of the universe, fairly natural one. There was the Earth, and there was everything that wasn't the Earth. And everything that wasn't the Earth obviously went around the Earth. You stand there, watch the moon night after night. It's moving with respect to the distant stars in a way that makes you think it's going around you, which it actually is. You stand there and watch the sun do the same thing. You might logically think, hey, the sun must be going around us. You stand there and watch Jupiter move night after night after night, and over the course of 12 years, see it sweep its way around the sky. You might naturally think that it's going around us. So can't actually blame them. In our hearts, we all think we're the center of the universe. They just wrote it down in a more formal way. The complication is that if that's your model, the planets don't move the way they're supposed to. So here's an animation by Richard Pogg from Ohio State. Earth is in the center, there's the sun, and I would especially encourage you to keep your eye on Mars up at the top. In the Ptolemaic world, they all quietly orbit around. But if you watch Mars over the course of a year or two, every so often it appears to go backwards. It moves into retrograde motion compared to the Earth. And so if you want it to be moving around the Earth, it can't be doing circles. It's got to be doing these incredibly weird and elaborate curlicues. The model in which the Earth is the center of the universe actually does a really bad job in detail of predicting things like where Mars is going to be next month or 6 months from now. It's no longer a simple view. Whereas a model that puts the sun at the center actually manages to reproduce those behaviors. It's less satisfying to our egos, but it does a better job of matching the observations in terms of astrophysics. And these concepts have been floating around for a while, but really the set of people who finalized them, Copernicus got the credit for really saying, oh yeah, let's put the sun at the center, but still had the problem that his version of that couldn't do a good job of predicting where Mars would be next month, because he assumed that all the planets would just go around the sun in simple, perfect circles. Really what satisfied it was the tag team of Tycho and Kepler, who I think of as the first astrophysicist, someone who has a physical model that can be tested with observations, that would be Kepler, and the astronomer, Tycho, someone who made observations, or in his case, paid other people to make observations, night after night. Tycho's hobby basically was paying people to measure where Mars was every night. That produced a beautiful data set that every theory Kepler came up with could be tested against it. And Kepler said, all right, we're going to keep the sun at the center, but the planets are going to move around ellipses. They're going to obey certain laws that I can write down. I don't know why they obey those laws, but he could write them down as equations. And he could finally say, yep, that's where Mars is going to be next month with unprecedented accuracy, and say his model worked in a way that Ptolemy's didn't. And to scientists, that was really the nail in the coffin. That was what confirmed a view in which the Earth was no longer the center of the universe. They did math. They had graphs. The book is full of beautiful hand-drawn early graphs that could show to people who understood mathematics that the sun was at the center. But the other person who was involved in this was Galileo. So not the first chap to build a telescope, probably not the first chap to look at stuff in the sky with it, but certainly the published first, which is basically how you get credit for these things. And of course, one of the very first things he did with his telescope was look at Jupiter. Natural choice. It's pretty bright, hard to miss it. And so he looked at Jupiter, and next to Jupiter in his notebook, he drew what he saw. He saw 4 little dots next to Jupiter in his first night of observing it. He said, all right, that's interesting, but they're stars. There's stars all over the place. I found 4 stars next to Jupiter. But he looked again, and even though Jupiter had moved, those 4 little dots were still there. And he looked again and again and again, and those 4 dots were always there in different positions that he rapidly realized meant they were orbiting around Jupiter, that Jupiter had its own moons, Jupiter had its own system, not everything in the universe rotating around the Earth the way people had believed before. Jupiter was an object. It had heft, it had size, it had its own system of moons. There were other worlds. And it's interesting to note that compared to Kepler, who convinced all the scientists, Galileo was the one who got into trouble with the church. No, there's no like historians of science in the room right now, so I can make sweeping generalizations. Good. Okay, so a variety of theories for this. One theory, he was in a place where the church was more powerful during the eras with the Catholic Church in particular. That was probably bad. He was a jerk. That probably also helped him get into trouble. But there's also something about what he did was simple. He looked through his telescope and he saw a bunch of dots. Anyone could do that and see that things were moving, that they still move not around the Earth. And it's interesting that that was what caught the imagination to the point where the church thought he was a troublemaker and had to be locked up. It's a very bad sign when scientists compare themselves to Galileo, so I'm not doing that. But there is something about actually looking and seeing things moving that's compelling to me in a way that lines on a graph aren't, which is what the core of this talk is going to be about. So when they did all this, we had I mean, before Copernicus, really, in some sense, we only had 5 planets in the solar system because they didn't realize the Earth was a planet. Post-Copernicus and Galileo, we had 6. For a while, we had 9, like when I was in graduate school. We've cut back to 8 for reasons you're all familiar with. I can live with that. What's interesting to look at, though, are some of the properties of these planets. So one, and this will be important later, there may be a quiz, is how long they take to orbit the sun. The closer a planet is to the sun, the less far it has to go, and the faster it goes. So Mercury goes around the sun in about 3 months. Pretty fast, we thought, by the standards of the time. Earth goes around the sun in how long? 1 year. Depending on how you measure, yeah, you can get a day or 2 off, depending on motion of the, how you calibrate these motions. Jupiter takes about 12 years, 30 for Saturn, out to 165 for Neptune. So closer to the sun, fast. Nice, easy relationship. But the second thing you might notice about these planets is they look different in 2 categories. Astronomers naturally always sort things into 2 categories. The solar system is great for that. In the outer part of the solar system is where all the big ones live. We're unimaginative. We call them giant planets because they're big. We now know they're mostly made out of gas with maybe a little bit of ice and rock in the center. They're very clearly different from the planets in the inner part of the solar system that are mostly made out of rock with an atmosphere of varying thickness. You can stand on them. There's this clear binary distinction between inner and outer solar system. And when I was in graduate school, I was taught this was what every other solar system was going to look like, that the laws that produce these planets, the process had to be the same everywhere. And in hindsight, that's not as embarrassing as Ptolemy, but it's not a great moment either. The idea that the only kind of solar systems there could be as twins of our own turned out to be spectacularly wrong. So how did we find it? How did we find out it was spectacularly wrong? The first detections of planets relied not on seeing the planet, because that, as I'll talk about more in a bit, is hard, but on their motion. So if you have a planet and its star orbiting in response to gravity, the planet orbits the star, like I just said, the Earth orbits the sun, but not really, actually. What actually happens is they both pivot around the center of mass, the place in between where the mass of the 2 planets balance. In the case of our solar system and Jupiter, that center of mass is still inside the sun, but it's right at the edge of the sun. So the sun wobbles every 12 years by about the diameter of the sun. It wobbles every year by a smaller amount as the Earth's gravity tugs it. It wobbles every 3 months as Mercury's tugs it around. The sun is always moving. And even if you couldn't see the planet, you could imagine looking at that motion and realizing there has to be something there whose gravity is tugging on the star. And how much it's tugging will tell you how big the thing it is, and how long it takes to go around will tell you how far away from the star the planet is. How do you measure that wobble? We actually mostly measure it as a velocity through Doppler shifts. The spectrum of the star shifts very slightly redder or very slightly bluer as the planet goes around it. Very slightly means for Jupiter in our solar system by about 7 meters per second, so kind of brisk human walking pace. For the signal the Earth puts on the planet, it's about 10 centimeters per second, which is like a brisk walking pace for a medium-sized lizard. But we can measure motions that accurately. 7 meters per second is easy with our spectrographs. And in fact, at Lick Observatory, we'll say in a moment, we did a whole bunch of these. So we can measure these wobbles of the stars and infer the presence of planets. When that happened, there were lots of beautiful press release pictures. We discovered a planet called the New York Times. Here's a planet. There's a a moon next to it that is evaporating for some reason, for reasons we'll talk about. People get very excited. But of course, that's not what we actually saw. What we saw were lines on a graph. On the left is a plot of the velocity of the star 51 Pegasus versus time, and measured over a series of observations in 1994 and 1995, they showed that it was wobbling. And in the process of seeing it was wobbling, discovered a couple of extraordinarily interesting things. How much it was wobbling tells you how big the planet is. It was wobbling enough that it required a planet the size of Jupiter. Jupiter exists. That's not really a surprise. The surprise was how fast it wobbled. It went around every 5 days. Remember I said Mercury, fastest thing in our solar system, takes 3 months. So this planet is much closer to its star than Mercury. And the idea that a planet the size of Jupiter could be huddled up right against its star, was kind of astonishing. And Mayor and Kellos got the Nobel Prize for this, partially for the precision of their measurements, but in some sense, more for the courage to believe that they had discovered something very different than anyone else. And in fact, there were groups looking for planets who had the ability to detect planets like Jupiter who didn't bother analyzing their data because they said, well, it'll take 12 years before we see the signal. We're not in a hurry. We'll get the graduate student to look at it next year. And so actually, once they announced this, planet number 1, basically planets 2 through 6 were data that were sitting in people's drawers that they hadn't been as brave as Mayor and Kellos to look at and analyze properly. So that's why they get the Nobel Prize for this, for the willingness to see that an observation that didn't fit everybody's theories was actually true, which is the finest thing you can do as an observational astronomer. And that's why this planet looks like this in the picture. It's huddled up against its star, so its moon is evaporating, which seems unlikely to me. It just wouldn't have a moon, but artists' renditions. But again, we don't know that. The Doppler signal just measures how big the planet is. So they discovered a planet huddled up against its star in 4 days. A whole bunch more were discovered. They're Jupiters that are close to their star, so we call them hot Jupiters. We're really bad at names. It'll be a recurring theme as we go through this. And they really upended theories of planet formation in a way that hasn't actually caught up since then. So that's planet way number 1. Planet discovery way number 2, which I'm sure you've had people talk about, but I'm going to explain to you anyway, is what we call transits. In that case, if you have a planet orbiting around a star, and the planet's orbit happens to line up so it passes in front of the star, planets are opaque, and so the star will get a tiny bit fainter for the 3 or 4 hours it takes it to move across the surface of the star. I bet people in this room saw this during the transit of Venus, for example, 10 years or so ago. How much fainter? For a Jupiter-sized planet, it's at about 1%. There are probably people in this room who've actually measured these kind of transits. You can do that with equipment, with modern equipment in a fairly straightforward way. For a planet like Earth, 0.01%, harder to do that except in space, but these signals are pretty strong. Of course, you have to get lucky to see it. If the orbit is aligned like this, you won't see a transit. Like this, you won't see a transit. Has to, like this, only people in the second row of seats see a transit. People in the first row don't see a transit. To have an odds of seeing this, you have to look at 1,000 or so stars. Old days, that would mean you needed 1,000 graduate students. Modern days, with computers and big digital cameras, we can look at 100,000 stars. And of course, the NASA Kepler mission, the triumphant dominant version of this, looked at a field in the sky with 100,000 stars day after day after day, looking for these transits with enough sensitivity to see planets like Earth. The TESS mission, the modern version of it, is looking at an even larger sample of stars. But you can also do this with 10-centimeter telescopes, as long as you have a wide enough field of view to look at thousands of stars at once. Or if you already know there's a transit and you know where to look, and you want to follow it up. So modern transit techniques found hot Jupiters. They found smaller planets and smaller planets, pushing out towards close but not exactly like the Earth. But getting in there. A lot of what they discovered were objects whose size is in between the Earth and Neptune. So again, this idea that our solar system is everything wasn't quite right. We have a big gap in size between Earth and Neptune. Lots of the Kepler planets fill that in. And if you're an optimist, you call them super-Earths because they're big Earths. If you're a pessimist, you call them mini-Neptunes because that would be less exciting than a super-Earth. And you call the New York Times and you have your press release to say, we found one and it's right in the Goldilocks zone of its planet, of its star. Could have liquid water on its surface. Maybe it's got clouds and deserty things going on. Again, what we know is it's about this big, and this is how long it takes to orbit. We don't know anything else about them in most of these cases, or call them mini-Neptunes. So there's a lot we don't know right now. We don't really have a good consensus theory of planet formation. Maybe there's several different ways solar systems form. Maybe ours is an outlier. Maybe ours is very typical. We don't know a lot about the outer parts of solar systems. I'll return to that in a moment. What is a super-Earth? We're starting to learn with the James Webb Space Telescope, but it's still hard. And more than anything else, are there a lot of rocky planets that have thin atmospheres that we can stand on? We have not detected an atmosphere around a rocky planet yet, even with the James Webb Space Telescope. Clues, how would you figure this out? Well, if you can measure the composition of a planet, you could at least say, is it rocky with an atmosphere? Even the giant planets you can learn things about. So the sun, 71% hydrogen, 27% helium, 2% other stuff, literally every other element in the universe. Jupiter is close, but not exactly there. The difference between Jupiter and the Sun is Jupiter has about 3 times as much other stuff in it, as much carbon, oxygen, probably iron and silicon, though those are hard to measure. So it's only 68% hydrogen. That little difference tells us that Jupiter isn't really a failed star. It didn't form the way the Sun did. Somehow it formed through a process that started with solids and then turned it into a planet. For Neptune and Uranus, they had a similar process but didn't get as much hydrogen. And then in the inner solar system, of course, hydrogen is incredibly rare. There's very little hydrogen and incredibly little helium on the Earth. It's pretty much all other stuff. And so that process that preferentially selects for solid materials is a pretty good one if you want to live on a solid planet. How does that work? We think planets form out of disks of gas and dust. This is a real image from the ALMA Radio Observatory showing a star surrounded by a disk of gas and dust with gaps in it where maybe planets are forming, and where we can see at some places in the disk there's more rock, other places in the disk there's more ice or more hydrogen. The mix of where you're forming kind of tells you what the composition of your planet will be. And so by studying the composition of extrasolar planets, we can begin to have clues as to how they formed. We do that through spectroscopy. If you shine a bright light through a cloud of gas, the atoms in the cloud of gas absorb particular wavelengths of light that tell you what the gas contains. And conveniently, that's very handy if you're in a lab, because you just put a laser behind your piece of gas or a bright light bulb, measure its composition. Sounds a little hard to do in space, but we actually can do that because there are bright light bulbs out there. They're called stars. And there's things with clouds of gas around them. They're called planets. If you line them up right, you can measure the composition. And what the composition is tells you what something's made out of. Sodium, the low-pressure sodium lights we're all familiar with, helium. Every atom, every molecule has its own signature. Solid objects like incandescent lamps give off continuous, every color of light. Mercury lamps give off different ones, and so forth. This can be done for the transiting planets. At the moment you catch the transiting planet when it's in front of its star, some of the rays of light from the star don't get to you at all because they hit a planet. Some rays of light from the star, most of them, get to you because they didn't hit a planet. A handful of the rays of light pass through the star's atmosphere and in the process pick up these absorption signatures of what it's chemically composed of. So there's a bunch of other people who could give you a long talk about how you do this with the James Webb Space Telescope. It's an incredibly powerful technique. Right now, it's letting us measure the composition of some of the giant planets and not quite the super-Earths. They're still, and the single biggest limitation of transits and Doppler techniques is they only work when you're close to the star. The odds of it lining up just right really drop if the planet's way out here. Much higher chance of it lining up just right if it's orbiting close to its star. And transit and Doppler techniques really only work if you observe the thing wobble or observe the planet block the star, ideally 3 to 4 times. First time, if you just see the star get fainter by 1% once, maybe a bird flew in front of your telescope. You see it a second time, could be 2 birds. You really want to get 3 times exactly spaced by the same amount, and 4 would be nice. The Kepler space mission that dominated this field lasted for 3.5 years before the warranty ran out and the gyroscopes broke. And so it could barely see 3 transits by an Earth-like planet, and in fact never got to 4, which is what you'd really need to nail it. In the end, it couldn't see Earths. The statistics of planets are also clues. The fact that you get giant ones in the outer parts, small ones in the inner parts, like I said, tells us something about how planets form. But again, with the transit techniques, the outer parts are inaccessible. And so a third technique, direct imaging, begins to bear on all of these by studying the outer parts of solar systems by measuring the composition of planets. So what is direct imaging? Way to study the outer parts of solar systems by doing images, by actually looking at a star and next to it seeing the faint little dot that's a planet. That's hard. The analogy I'm required by astronomy law to use is it's like you're looking at a lighthouse, and next to the lighthouse you're trying to see something extremely faint, like, say, a firefly. And that's about the right ratio for the planets that our group discovered. Fireflies are about 1 million times fainter than a lighthouse, give or take some assumptions about geometry. 1 million times, pretty hard to overcome when the firefly is right next to the lighthouse. Even more so when you do it from the ground. So if you look at a star through the Earth's atmosphere, as you're all familiar with, the Earth's atmosphere distorts it. The turbulence in the Earth's atmosphere turns the sharp image of a star, like the one on the left, into a big moving blob of speckles and turbulence if you magnify it enough. If you look at Neptune from a pretty good site, with a pretty good camera, you can kind of tell that it's roundish, and maybe it has a bright blob on it, give or take. So we work on fixing that. Some of the first stuff I did as a postdoctoral researcher with Claire Max, who was my mentor, was develop the technology of adaptive optics. Adaptive optics uses thin mirrors that can change their shape 1,000 times a second. Usually, I think Phil Hines came here and talked about big mirrors, but the ones we use right now tend to be small mirrors, so not the primary mirror of the telescope, but you refocus the light on a small deformable mirror, changes shape 1,000 times a second. We have a wavefront sensor, something that can measure the distortions of the light. We have a computer and some math so that those distortions turn into commands to the deformable mirror, and then ultimately sharpen up images as seen by a science camera. And there's Claire Max demonstrating at Lick Observatory with the first laser guide stars also. And so it'll turn something like this, Neptune, into something like that. These are actual Keck adaptive optics images of Neptune taken with a pretty good telescope. So we can reach the theoretical limit of resolution using adaptive optics. That's the first problem. We did this with the Keck telescope, primarily the one on the left initially, and started a large-scale Keck telescope search for young planets. Why young planets? I'll get to the young in a little bit. So here is an image of a star with adaptive optics taken with the Keck telescope. Pretty sharp, nicely in focus. Very happy with that. But planets are really faint, so if I want to see it, I have to overexpose the star. If I overexpose a star with the Keck telescope, I get something like this. When I'm talking to less expert audiences, I tend to liken it to lens flare when you take a picture looking at the sun. It's a mix of structure from the secondary mirror supports of the Keck telescope, which are six-sided, from the segments of the Keck telescope, from polishing errors because the mirror isn't perfect, from leftover atmospheric turbulence because the adaptive optics isn't perfect. Every one of those little streaks of light is about 1,000 times brighter than Jupiter would be, so hard to see Jupiter against that. So the second trick we did is we looked for planets that are brighter than Jupiter. Not, it turns out, bigger than Jupiter, that doesn't help, but young. So we don't completely understand when planets form, but we're sure it's a pretty energetic process, and that young planets are going to be hot. A brand new Jupiter would have a temperature of about 3,000 Fahrenheit. A 10 million year old Jupiter would have a temperature still of about 1,500 degrees Fahrenheit. You have to wait 4.6 billion years before it cools down into the minus 200 range. So if I could look for Jupiters that were 10 million years old, they'll be temperature of 1,500 Kelvin. They'll be glowing, especially at red and near infrared wavelengths, much brighter than they would be if they were just reflecting sunlight. So we started a project where we'd look at stars that we knew were 10 million years old, because their planets therefore had to be no older than 10 million years, all the way up to about 100 million years, because those we could see planets around. Here's one of our first images. You can see all the diffraction from the Keck telescope, but a little dot that I've conveniently put a circle around. We got excited, found a planet, but you want to be cautious. Maybe it's faint because it's a planet. Maybe it's just faint because it's a star that's a lot farther away than the main star. There are a lot of stars out there, so it turns out it was a star that was just further away than the main star. And with a little bit of observation of its motion, just like Galileo did, except we got the sad answer, we could prove that it was just a star. We did this again, found a background star, found a background star, found a background star, looked at a binary star and found a background star, found 3 background stars orbiting around something, which saved valuable time, found another background star. We looked at about 200 stars, and we're beginning to get a little discouraged, but my postdoctoral researcher, Christian Merois, young and energetic, continued the search, and ultimately we found something. This is a real Keck image of the star HR 8799. It's about 6th magnitude in Pegasus. The star is in the center, partially blocked but not perfectly, so the blobs you're seeing in the center are residual light from the star, still there after a lot of image processing. The giant arrows, of course, do not exist in space, but they show you where the 4 planets are and the way they're moving. Star is an F0, so it's about 50% more massive than the sun. The planets have temperatures which we can measure of about 1,000 degrees. The one at the edge is a little bit fainter, and from that we can infer that their masses are sort of 3 or 5 times the mass of Jupiter, a whole other solar system seen from outside. Discovered these, the fourth planet we discovered in 2010, the first 3 we discovered in 2008. We've been watching it ever since. Here's the 2009 version of the image, which means we can watch them move. So this lovely animation that Jason Wang, who's now a professor at Northwestern, put together with our data, shows us about 10 years of the planetary system orbiting. And they're doing exactly what Kepler said they would. The one close to the star is moving fast. The one far away from the star is moving slowly. They're obeying Kepler and Newton's laws. That's not a surprise. Those laws are universal. But the fact that we can see Kepler's laws in real data over the course of a professional lifetime is still like the most amazing thing that I've gotten to be part of as an astronomer. I actually need to update this because we got a 2025 image about a month ago that's going to have to go into the movie. So we had our press release pictures because that's what you do. Okay, we didn't really see the planet as having big glowy clouds. But if you can see the planet at all, like in this image, you can feed the light into your spectrograph. And we did that. And here's a near-infrared spectrum of the planet at wavelengths from 1.6 to 2.4 microns. Most of the light coming from it is probably coming from hot clouds of liquid metal deep in the planet's atmosphere, where they have temperatures of about 2,000 degrees or so, iron droplets and things like that. There's a big area where there's no light. That's because water, vapor, and hydrogen absorb those wavelengths of light. Water you shouldn't get too excited about. It's a planet the size, 3 times the size of Jupiter, the temperature of 1,000 degrees, so water means superheated water vapor. Not going to be living on it, but we can tell that the water and the hydrogen are present. We see absorption from carbon monoxide. We didn't see absorption from methane, which is kind of a surprise. Computer models said there should be methane. And that combination actually tells us a lot about what's going on in the planet. The atmosphere is hydrogen, water, carbon dioxide, and methane. There's dense hot gas, clouds of liquid metal deep in the atmosphere. We can even tell that the atmosphere is circulating, that the circulation from hot interior to upper levels, kind of convection plumes, are destroying the methane and making carbon monoxide. In other planets, you can see cold, high clouds of silicate, of sand-like particles. You can just tell a lot about these planets. Overall, these ones are a little more star-like than Jupiter. Their composition is closer to the sun, and they kind of live out here. So again, maybe a clue that the process that makes these big planets is more like the star-making process than the planet-making process. We wanted to see, though, something really like Jupiter. That system is much bigger than our own. The outer planets are way out past the edge of Neptune. But if you remember the lens flare in the movie, we can't quite get close enough to see a planet like Jupiter, even with Keck, even with good adaptive optics. So in parallel, we were working on an instrument to go on the Gemini telescope, an 8-meter telescope in Chile, that would image planets. We're bad at names, so we called it the Gemini Planet Imager. Here's a picture to scale of it. I was talking about telescope instruments with people a little bit. The Gemini telescope only takes instruments at its Cassegrain port. They have to weigh exactly 2,000 kilograms, not even 2,020, because then the telescope falls over or something. So extremely weight and volume constrained, extremely power constrained, only allowed 2 kilowatts, very tight environment to work in, but good engineering went into it. The Gemini Planet Imager combines an infrared spectrograph, because really I don't care about seeing the dots, I care about what they're made out of, built by UCLA. A really advanced adaptive optics system that my former group, when I was there at Lawrence Livermore, built, one of the most advanced in the world. A set of special masks called coronagraphs to block the star and let you see even closer, built by the American Museum of Natural History. And a lot of software built by a group in Canada, the Hertzberg Institute, and mechanical structures that hold it all together, as shown in this CAD diagram. Here's the instrument coming together at UC Santa Cruz in 2010. We did final assembly in a clean room because a speck of dust might look like a planet, which would be embarrassing. It's not a clean room in this picture, which is why there's people with beards there. But after that, we wiped it down and clean roomized it. Also around that time is when my daughter was born, which is a complicated time to be doing a large scientific research project. But fortunately, we had a large, extremely good team, and so I just got to sleep and pet the dog. Here's the final assembly. This is the infrared spectrograph that UCLA built going in. It's a little hard to tell on this projector, but it is extremely red. midlife crisis red, I think technically. It was painted by a company that mostly does sports cars, which is what you do if you're in LA and you need something big and metal painted, I guess. As I said, Gemini is a Cassegrain telescope, so instruments attached to the back of the telescope, which is not many modern telescopes. You have other options. We didn't, which means it's going to move all over the place as the telescope moves all over the place. You'd like to know nothing falls off, so we put it on a crane and tipped and tilted it over 90 degrees worth of motion, 180 degrees worth of motion. Nothing fell off. Maybe a couple of things didn't. We tightened the screws. More precisely, it actually not only needs to not fall off, it has to stay aligned to about 0.05 millimeters over all of that motion. And so we used this to validate the engineering to say that the whole structure wouldn't flex or bend at that level. Similarly, especially in Chile, temperatures can go from about 10 to 15 degrees down to about -5. Has to stay aligned to within 0.05 millimeters over that temperature range. And so we built a giant meat locker around it, and we chilled it down to -5 Celsius, showed that the computer still works, showed that the mirrors stayed the right shape, showed that it could keep operating over that range. And then we put it in a box, 10 years of one's life work going into a box. By then, my daughter was old enough to help with the process. And so we loaded it on a truck. Again, 10 years of your life's work going on a truck, kind of exciting. You can't drive to Chile, so the truck actually just took it to LAX, and then it got loaded on an airplane that flew to Chile. Arrived at the Gemini South Telescope on Cerro Pachon in the southern Andes, got unloaded, and then sat in the basement for 3 months because we were a little early compared to when they thought we would arrive. And the team went down and unpacked it. At that point, we acquired our mascot. That would be the adorable Chilean Andean fox, or Zorro, or Quailpo, excuse me, I can't pronounce it properly depending on who you ask. You can see it in the upper right on the logo. And then I went down and was reunited with the instrument and was happy. Here it is going on the back of Gemini. Gemini, as a complicated telescope, one of its virtues is it actually has ports for 3 instruments at once. So when you're putting a new one on like ours, you can leave it on the telescope for a while and they can keep using their ordinary cameras and spectrographs and then switch to ours for testing. Over the course of a year, we attached it, made it work for the first time, shook it down, and started to look for planets. The project to look for planets was called the Gemini Planet Imager Exoplanet Survey because we were using the Gemini Planet Imager to do a survey to look for exoplanets. Again, names aren't our strong point. Initially, we got to fly down to the observatory in Chile, which is just amazing. Increasingly, as the project went on, if you're just operating it with computers, you might as well stay at home. And so we started to operate it by remote control from places like a remote ops site that we set up at Stanford. Less exciting, more sleep, and you don't have to be away from the kid as much. And you can get help, so the dogs can come in and help you observe when you're at a site in North America. And here's members of our team, including Vanessa Bailey, who's now off being a project scientist for the next big NASA Space Telescope, and Eric Nielsen, who's at New Mexico State University now, and Percy and Calla, the dogs that we had at the time. In addition to building the instrument and operating it, we put a lot of work into our data pipeline. Actually, arguably, the best feature of GPI was we built a fully automated data infrastructure that in real time would take data, archive it, process it, develop images where they would do the analysis to see if there was a planet present or not and post it in the Slack chat as the night went on. That's actually probably our greatest advantage over other projects that were doing similar things. We could get our data reduced. We did not let our data sit in the drawer. We could get it reduced in real time to see if planets were present. Work led by Jason Wang, same guy who made the movie, who's now at Northwestern. So over the course of 4 years, we looked at 540 stars. The image in the middle is actually what you see over the course of a night. It's building up more and more sensitivity, looking for things. There's a lot of structure in it that's left over lens flare, but you can see a hint of a kind of horizontal ring. And I'm about to show a movie of all the stars that we looked at, and you might keep your eye open for things like that. So here's the Gemini Planet Imager survey starting in 2014. Oops, sorry. Let me let the movie run. Animation's always a problem. All right. We'll get started. There we go. So surveying the southern sky. If you look on the right at the images, often you'll see little dots appear. Most of those are stars or background stars, but occasionally some of those dots that are visible are planets. If you're fast, you might also see some rings or partial rings or edge-on rings, and I'll talk about what those are in a second. The circles show the stars we observed. One of them you'll notice we observed again and again and again because that's where we discovered a planet, and we wanted to watch its orbit and make one of these movies. So 540 stars over the course of a year. So I've sped up the movie a lot so you don't get to read the credits, but I can run it again if you really want to see it. I showed you those rings. I'm not going to talk about them a lot, but they're kind of awesome. Those are asteroid or comet belts. So in addition to having bright young planets, young stars often have a lot of asteroids and comets. They haven't really settled down. So not only do they have a lot of them, they're colliding with each other all the time and producing a lot of dust. The asteroids themselves are invisible, but the dust they make when they collide with each other is visible and traces the presence of these asteroid or cometary belts. I actually like to use this as a trick question for people. In our solar system, brightest thing in our solar system seen from outside is the sun, obviously. Second brightest thing in our solar system, if you're looking at our solar system from 100 light years away or so, would be what? Zodiacal light. Yeah, I've spoiled it by doing the wrong order, but you also all know this. So even in our solar system, there's dust left behind by asteroids and comets. Because these systems are so young and chaotic, their zodiacal light is 1,000 times brighter than ours. It'd be actually pretty easy to see if they had planets you could stand on, which they don't because they're 10 million years old and their planets are getting smacked by asteroids all the time. So this is basically zodiacal light or Kuiper belt equivalent thereof around other stars. And people like Paul Kalis, Tom Esposito have written a lot of papers studying this with GPI. But my field is planets. So these are our planets on top. We had simulations that said we were going to find 20 to 30 planets. We saw 6. 5 of them were previously known, but we're allowed to count them because our survey was done blind. We didn't prejudice ourselves towards known planets. One of them was a new discovery. On the bottom are 4 brown dwarfs. A brown dwarf is an object that's bigger than a planet and smaller than a star. We got 4 of those for a total sample of 10. And that told us something. It told us giant planets were rarer than our models thought they would be, that they're not as common as, say, the hot Jupiters. And that's interesting. The orbits of the planets and the brown dwarfs are different. That tells us something. They're really different kinds of object. It's not that a planet is a small brown dwarf. They really are fundamentally different than each other. And we can study their spectra. The one planet we found, 51 Eridani, had a spectrum that basically looked like Jupiter. If you showed it to somebody 50 years ago, they would say, yep, that's Jupiter. It's got an atmosphere dominated by methane. Again, we had our press release picture, but we can tell from the shape of the spectra that it's partially cloudy, that it's got silica clouds that cover part of its surface. In between, you see deep down into the hot interior. The atmosphere is not circulating as much as the other planets' atmospheres are, probably because it's colder. We can study the composition in detail. So it's still getting into the regime where we're not quite at Jupiter's, but we're getting pretty close. We'd really like to see a Jupiter, something that's actually right in the Jupiter situation. Boop. There we go. We still have a little bit too much lens flare. We also, as I said, we look primarily at young stars. There's not an infinite supply of young stars. Well, there is, because it's the infinite universe. There's not an infinite supply of young stars that are bright enough and close enough for us to look at. The 540 stars we looked at kind of exhaust the southern hemisphere's reservoir of young stars. The Gemini telescope is called the Gemini telescope because there are 2 of them. The second one is on Mauna Kea in Hawaii, and so we're currently in the process of moving the Gemini Planet Imager from Chile to Mauna Kea in Hawaii. Also in that process, we're upgrading it because it's now more than 10 years old. Computers have got better, mirrors have got better, spectrographs have got better, and so we're rebuilding it into what we're going to call GPI-2. And then we're updating the logo from the adorable Chilean fox to the adorable Hawaiian goose instead. One of the best parts of becoming a senior scientist is you don't have to do this anymore. And so this project is being led primarily by people who once upon a time were my students and postdocs and now are amazing scientists themselves. Jeffrey Chilcote, who's at University of Notre Dame, Quinn Konopaki, she's at UC San Diego, Dmitry Savransky, Christian Marois. I'm just kind of the grumpy old guy who gives them advice and looks over their shoulders as they're doing this. With luck, GPI-2 will ship to Mauna Kea in around the middle of next year, going on the Gemini North Telescope, excuse me. Now that I'm in charge of University of California, I'm in an interesting position that I'm more cared about the Keck telescope And so I'm sort of have this self-rivalry because we're also upgrading Keck's ability to look for extrasolar planets like this. That's happening with an instrument called SCALES that we're building at UC Santa Cruz even as we speak. So I mentioned young planets. So the sun, I did all these temperatures in Fahrenheit because this was a general purpose public talk. Temperature about 10,000 degrees Fahrenheit means it glows in yellow light. That's what 10,000 degree objects do. Red dwarf stars, 5,000 degrees, glow in kind of red visible light. The young planets, like the ones I've shown you so far, with temperature about 1,000 degrees, glow in the red to the near infrared. 1,000 degrees is the temperature of the element on your stove. So you can actually see visible light from it, and at near infrared wavelengths, not quite serious infrared, it glows extremely brightly. So near infrared instruments like GPI can see these planets. Older planets, lower mass, but especially older, might have temperatures of about 40 degrees Fahrenheit or 300, 400 Kelvin. Objects with, that's the GPI range. Objects with temperatures of 40 degrees Fahrenheit are things like dogs. Dogs do not glow as seen in visible light, as you're probably familiar with if you actually have a dog. They do glow at thermal infrared wavelengths, or if they're possessed by evil. But I think this is just a thermal infrared wavelength picture rather than a possessed by evil picture. And so the SCALES instrument is a thermal infrared camera to look at cold or cooler planets at wavelengths that we haven't been able to access before from the ground. And not only is it a camera, cameras are okay, it's a spectrograph. The complicated, labored acronym Andy Skemmer, who's the PI of this, is better at names than I am. It combines a slicer and an array of lenslets to make a spectrum of every pixel that it's looking at, letting you discover a planet and measure its chemical composition at the same time. And in the image on the right, the planet appears as you move to more red and red wavelengths. At least I think that maybe there's not a planet in that one. All right, it's supposed to appear. It's under construction at UC Santa Cruz right now. If anyone wants to come see it, you have about 2 months because we're going to ship it to Keck at the end of January, but we're happy to host visits. And it will study still Jupiter-y planets, maybe down to Saturn masses, and measure their chemical compositions. Last thing I want to talk about, though, is the step towards getting planets like Earth. So it's amazing that we can measure the composition of a Jupiter or a super-Earth. Even more amazing would be to measure the composition of a planet like Earth. The problem is planets like Earth are tiny compared to the Jupiters. The young Jupiters are about 1 million times fainter than the star. That was the firefly next to the lighthouse that I mentioned. Earth is a single-celled bioluminescent algae next to a lighthouse. It is 10 billion times fainter than the star. This is an analogy that Kate Follett, a professor at Amherst, came up with, doing the math carefully. That's pretty hard. And it has to be at just the right place. So if a planet is too far from its star, Mars in our solar system, or Pluto, it gets cold no matter what size it is. If a planet's too close to its star, Venus or Mercury, it gets too hot. Really, to be just the right temperature, you have to basically get as much sunlight as the Earth does. Where you have to be to do that depends on what kind of star you're orbiting. In this graph, I have different kinds of stars vertically, star like the sun, star much hotter than the sun, star much colder than the sun, and then distance compared to the star. Earth sits here, just right, gets the right amount of sunlight. If I'm orbiting a star like the sun, I basically have to be where Earth is to be not too hot or not too cold, give or take. On the other hand, if I'm orbiting a colder star, I have to be much closer to it, huddled up right against it to get enough sunlight. If I'm orbiting a hot star, I have to be further away. That's kind of good news for the transit people, actually. So we call this, because you're not too hot, not too cold, the Goldilocks zone. There are other reasons we call it that, being where you're most likely to find bears orbiting around other stars. But it'll depend on the mass of star. So if you want to be an Earth orbiting a low-mass star, you have to be very close to it. That's actually pretty good for transiting people, and the James Webb Space Telescope might be able to get the spectrum of an Earth in the Goldilocks zone of a low-mass red star. It's also good for imaging. If you're close to a star like that, and if the star is really faint, like a little red star, you're only 100 million times fainter than the star instead of 10 billion times. You're like a cluster of bioluminescent algae. That's almost easy. But you're really close to the star, which means you need a really big telescope to separate, to resolve the planet from the star. And so many of us have proposed building really big telescopes. The one University of California is involved in is the 30-meter telescope. It would have the ability maybe to study Earth-like planets in the Goldilocks zone of red stars, really close to them. On the other hand, if you're in the Goldilocks zone of a sun-like star, you're at the 10 billion, you're at the bioluminescent algae. We cannot build an adaptive optics system good enough to see 10 billion to 1 to see algae. No matter how good our adaptive optics is, the laws of physics hit their limits, even with a 30-meter telescope. We can't do this on the ground, in particular because the damn atmosphere won't hold still. Even if I'm measuring it 10,000 times a second, it always moves in between my measurements. My correction for the turbulence with my deformable mirror is never perfect. Solutions to this have been proposed. The easiest one is to get rid of the atmosphere. People get mad if you get rid of the atmosphere on the Earth, so ideally you do that by putting the telescope into space. The proposed next big NASA mission is something that is an observatory we're building to look for worlds that might be habitable. We call it the Habitable Worlds Observatory because we're still bad at names. Better than the name the Decadal Survey gave it, which was the Large Infrared Optical UV Telescope. So a step forward in the naming convention. What would it be? It would be a large mirror so that you can separate planets from their stars, at least the size of the James Webb Space Telescope. Bigger would be nice, but bigger is expensive, so let's settle for at least the size. It's designed to be a very clean telescope. If you look at the diagram on the right, one thing you won't see are big spiders supporting the secondary mirror. The secondary mirror is the tiny thing near the bottom, off axis, off to the side. So there's nothing blocking the beam of the telescope to scatter light and hide a planet. That's quite important. It has coronagraph masks will have coronagraph masks to block starlight, designed to operate over a huge range of wavelengths because we want to study the composition of these planets in detail. It will have adaptive optics, even though it's in space, not because of turbulence, but because we can never make mirrors that are smooth enough to not have a little bit of lens flare, but we can make mirrors that will change their shape and smooth themselves and cancel out what lens flare is present. In order to do that, it also has to be incredibly stable so that the mirror doesn't distort not just over minutes, but over months, even as the telescope changes temperature. In fact, the requirement on the stability is about 30 picometers. The telescope has to stay the same shape at scales much smaller than the size of an atom over time scales like weeks. That's hard. It would be fair to say we don't technically know how to do that right now, but we know how to get close to it, and we know how to measure our ability to do that. And so I think we could actually build this on about a 15-year time scale, give or take, the federal budget cycle. When we build it, it's designed to look at about 100 stars. Finally, not young stars, but mature, nice, well-behaved sun-like stars in the immediate neighborhood, stars whose names you all know, relatively bright and relatively close. When it does that, first thing it's going to see is asteroid belts again. And from this standpoint, although the asteroid belts are fascinating, they kind of get in the way. I like them. They're a feature. They're a little bit of a bug. It kind of swamps the light from the planet. But you can still potentially see the little dots there. Some of those little dots are going to be Jupiter-sized planets. Some of them are going to be background stars. Some of them, in this image, though, you might be able to tell are different colors. We can image at different wavelengths and begin to get hints of what a planet might be just based on its color. And we might notice that that one, for example, has a planet that's a little bit blue. And so we'll go back and look at it, and we'll feed its light into a spectrograph. Over days, planets are so incredibly faint that it's going to take days or weeks to measure a spectrum. But the possibilities are so exciting, we're going to spend days or weeks doing it, like the Hubble Deep Field of spectroscopy. And when we do it, we'll see the same chemical signatures in this simulation by Jetta Arni, who's the project scientist for the Habitable Worlds Observatory. Instead of being due to super hot clouds of metal or methane or carbon monoxide, we'll see signatures from things like water, methane, but also, we hope, oxygen. Oxygen is what we call a biomarker. The only reason there's oxygen in this room is because they're plants. If you killed off all life on Earth, the oxygen would be gone in maybe 1 million years or so. I'm making that number up. It might be 100,000 years, but pretty quickly. In detail, there's a lot of argument about what combination of things could you make oxygen through non-biological processes. You probably need a bunch of different chemicals, but if we had an atmosphere like Earth, Habitable Worlds Observatory could measure it in a way that I think would be convincing to everybody that it would count as life. Will it do that or not? I don't know. This is my favorite quote from the Astronomy Decadal Survey, partially because I wrote it. We don't know the answer right now. The presence of planets like Earth, and especially life on them, could be something that's incredibly common. The laws of physics are the same everywhere in the universe. And so it's possible that we'll look at 100 stars and 10 of them will have life. On the other hand, the process that turned some primordial muck into algae that made that oxygen eventually could be incredibly rare. It is possible we are the only life-bearing planet in our galaxy, or within 1,000 light years. We have really no way to know right now from theory, because our theories of planet formation and life creation aren't good enough to make predictions, but we can build a machine that will observe it. If we look at 100 stars and see nothing, that tells us planets like Earth are rare, in which case we should be careful about the one we're standing on. We might be almost unique in our part of the galaxy. Or we look at 100 stars and one of them has that oxygen, that methane, that water, that carbon dioxide, that biological signature that finishes the revolution that Copernicus and Tycho and Kepler and Galileo started. Said not only are there other worlds, there's other worlds like us, and we're not unique in the universe. Either of them would be transformational for human beings, and that's where we're trying to develop the technology to get. So let me stop there and have a little bit of time for questions. Yeah, and people can wake up now too. So. Actually, you're all probably, because astronomers, you're trained to stay up when it's dark. You did better than many audiences with the lights down. So,
I have a question for you.
Yes.
So, if you're using adaptive optics and a space telescope, and the mirrors are deforming, and they're equal and opposite reactions and stuff, no friction in space, like, is it harder to track?
It is. Also, just because the measurements have to be so exquisitely precise. And so figuring out how you're going to sense the deformations is a complicated question. There's proposals to use lasers, like the telescope might have a network of lasers that measure the position of all of its mirrors internally. You can use the light of the star itself, because the star is pretty bright. There's even proposals to have another spacecraft that's formation flying 100,000 kilometers away that lights up the telescope's mirror with lasers. So they're extremely challenging sets of measurements. And in the end, actually, probably the ultimate measurement will actually be the images that come from the science camera that's looking for the planets, because that's where you want the wavefront of light to be perfect, and looking at the exact pattern of speckles and interference and lens flare to kind of reconstruct how you move your deformable mirror. In the baseline mission concept, even doing that will probably take a star that has a Greek letter in its name that's like 5th magnitude or something, or 4th or 3rd magnitude. We want to look for planets around fainter stars, so the model is you'll point at some star that has a gamma in its name, measure the distortions, move the deformable mirrors, and then freeze them. Then go look at the star you think might have a planet, and everything has to hold still in the week it takes you to do that. And that's probably the single biggest challenge in the mission. We can build mirrors that are precise enough, but can we get them to hold still for a week? That's an extremely challenging, extreme technical challenge right now. Yep.
The name HR8799, was that the galaxy?
That's the star's name.
The star.
Yeah. Harvard Revised, it's the Yale Bright Star Catalog, which for reasons I have never understood, HR stands for Harvard Revised, and how you get the history. It has a couple of other names, but we settled on HR8799, like all stars have multiple names, yeah. So the planets are HR8799, B, C, D, and E. One of the frustrations in the exoplanet game is you don't get to name the planets. I mean, if you find an asteroid, they let you name it. Asteroids feel pretty important. You should, you can name it after your cat. But I just get HR8799C or something like that. And admittedly, if I did get to name a planet, I would call it like Planet of the Flaming Metal Death Clouds or something like that. So it's probably good that they don't let me, but still kind of frustrating. We have 5 of them. Everybody in the team could have named a planet, but no. So complain to the International Astronomical Union and tell them discoverers should be allowed to name exoplanets. Yeah.
Knowing how things are developing, how quickly we're coming up with new equipment and so on, would you care to guess when are we likely to know whether or not the Earth is rare or common?
The timescale for Habitable Worlds Observatory, which is the mission that could do this, I think, Current missions really aren't quite good enough. Webb, there's like 3 planets Webb can look at and make these measurements, and I think we're not going to get lucky in those 3. So it really needs HWO. The plausible timescale for launching it is about 15 to 20 years, and that's set by a couple of things. Some of it is just federal budget. It's probably on the order of a $12 billion mission. I mean, if I had had this discussion a year ago, I would say that NASA could afford to spend, a typical NASA budget would spend up to $500 million a year on a big science mission. 12 divided by 500 gives you the time scale to launch the mission. But even if we had unlimited funding, we don't quite know how to make the mirror perfect. So the plan would be about 3 or 4 years of really nailing the technology and then designing a mission around it once you've updated the technology, and it will take about 10 years to assemble it and launch it. Hopefully it won't have some of the issues the James Webb Space Telescope had. There's a whole separate talk about project management that I could give. But yeah, I would bet 15 years if we have the national will, if we have a functioning science budget. I mean, as you're aware, the proposed presidential budget for NASA is basically at the we never launch another space telescope again level, which would be kind of bad. So it depends what happens. Yeah, middle back, and then I'll get to further back. Middle back, and then I'll get to back. Somewhere there.
So this is more about life in the universe than other planets.
Mhm.
But I was just wondering what you knew about Oumuamua, and wasn't there the confirmation that there isn't a lot of life in the universe to begin with?
So yeah, you're asking about Oumuamua, now 3I Atlas. These are asteroids or comets that are known to be interstellar, that they came from outside our solar system. That is, to my mind, that makes the top 5 amazing astronomy discoveries of the past decade. They're asteroids from another solar system, and we can measure their composition with telescopes. In 20 years, we'll be able to do sample returns from them. We could bring back a piece of another solar system and put it in a lab and study it, and that is awesome. There's a chap at Harvard who keeps saying they're aliens. He is wrong. But the fact that they're not aliens doesn't really mean life is rare. Most asteroids in our solar system don't have life on them, so it's not a surprise. It's the potential to be able to begin to address these questions. We could at least look at the chemical composition. You know, we know life is rare in our solar system. We have about 20 to 100 meteors that came from Mars, and again, no matter what you heard, none of them have life in them. But that doesn't mean it's non-existent either. So yeah. I was going to let the chap wait in the back.
Some of the systems fixed for the habitable observatory, like aperture, focal length at the coronagraph, passively cooled, what orbit, or
The decadal said it should be 6 meters, 6.5, largely because that's what we think we can afford. We know from James Webb that we can build 6.5 meters and that we could keep it in the cost envelope. The people doing the mission would like it to be bigger. So decadal survey I keep referring to, it's a thing astronomers do every 10 years to plan the next 10 years of astronomy and set research priorities. Because it's a survey to plan the next 10 years, we call it the decadal survey because we're bad at names. I was part of the committee that did it, and we said, you know, I know you'd like an 8 or a 10 meter. If you do that, you won't be able to do any other space telescopes. That's kind of imbalanced. We do it 6.5. Every time I go to a conference, the people on the mission are showing simulations and designs for an 8 and a 10 meter, and I just want to hit them with a damn book and say, read the book. You know, we thought we knew you wanted an 8 meter. We think you can't afford it. So baseline is 6.5. Focal length, I don't know off the top of my head, but it's pretty slow. It's pretty long. Because when you're off axis like this, when your secondary mirror is on the side, you pick up a lot of aberrations, and so you can't curve the mirror too sharply. So it's a long focal length, which does push the mission mass, the design mission mass up more than a so it's longer than the James Webb Space Telescope in that sense.
so it would be like Cassegrain, Ritchie-Gradian, Gregorian?
Definitely not Gregorian, because that would make it even longer. Off the top of my head, I think it's probably a Cassegrain, but I haven't studied the optical prescription. An off-axis Cassegrain, which is a bit weird in normal life, but something we know how to build. Segmented primary mirror, because we can't build a 6.5 monolith primary mirror that we can launch without breaking, or that is stable enough. Compared to James Webb, in the lights you can't quite see it, but if you've seen pictures of James Webb, it's got this sun shield, but then the whole telescope floating free. This has a complete tube around it, and that's because something that happened to James Webb in its second month is it got hit pretty damn hard by a micrometeor. You can actually see the distortion on the mirror where the micrometeor hit it. In a mission like this, where you need that mirror to be ultra stable, that would be bad. And so it has not just a sun shield, but a meteor shield around the tube to keep it from getting impacted. And then compared to James Webb's mirror is metal for various reasons. This would be a glass mirror, an ultra-low thermal expansion glass, because we want it to be stable at that level. Probably hexagonal segments. I like hexagons, but people are studying what the best exact geometry for the mirror is right now. So right now, these are straw men. What's actually going to fly will probably look different than the cartoons. The thing that we're going to do is take a design, show that it can do the science, figure out how much it costs, and then when it costs too much, figure out how can we adjust it and still do the science and remove the wish list. It also has to do a lot of non-exoplanet astrophysics because it will be the flagship, so lots of work is going into how it can study cosmology, galaxies, and things. I can't remember what order people have raised their hands in, so I'll apologize. I'll start at the front and work my way back again. So.
By the way, my undergrad was from UCLA, so you make me very happy if I keep mentioning UCLA.
It's where I did my PhD. It's where I did my PhD. It was a wonderful university to be at. They do awesome astronomy. So.
So, question. So let's say we find that blue speck.
Mm-hmm.
Now, Earth itself went through a lot of evolution. It was
Yeah.
inhabitable for a long time too. So if we find it, it's going to be too far away for us to go visit to begin with.
Mm-hmm.
What's our plan? So if we find few, let's say 15, 20 years
Yeah.
from now.
The evolution, we'll do this first spectrum. We'll say that it has life. Other people will disagree, and so we'll try to study the atmosphere better and better. Maybe we'll have a larger successor telescope or study other wavelengths of light. If you can get out into the infrared, you can learn a huge amount about the chemistry, and we'll show the chemistry is more and more Earth-like. Or not Earth-like. One of the brilliant things Giada's done, this is a simulation of Earth. She's made simulations of what Earth looked like 1 billion years ago, or 2 billion years ago, or 5 billion years ago. We know how Earth evolved, and we can tell the ratio of oxygen to carbon dioxide. So we'll be able to tell something, and you can look at the star and see how old the star is. So we'll be able to say something about evolution. The next, better and better chemistry. Ultimately, people are asking the question of how could we move from a dot to actually seeing continents on the surface of the planet. I didn't put it in this talk. I had a grad student when I was at Stanford who worked on that. To get that kind of resolution would require a telescope 1,000 kilometers across. Very hard to get. We can afford a 6 meter, hard to get 1,000 kilometers. There's two tricks. One of them is you combine multiple telescopes into a single big synthetic telescope, so they'd be flying in space in formation. That might work. The other one is there is actually a telescope in our solar system right now that is about 30,000 kilometers across. It's the sun. So the sun has gravity. Gravity bends light. The sun acts like a lens that's 30,000 kilometers across and focuses light. You asked about focal lengths earlier. The focal length of the sun is about 500 astronomical units. So you have to put your eyepiece out 10 times past the distance between Earth and Pluto. Takes a while to get there, but you could launch a eyepiece spacecraft, basically, that would fly out, get there 10 times the distance from the Earth and the sun, and be right where the sun focuses light, at which point you have a telescope big enough that it can actually produce an image where you can see continents, maybe even forests, with sort of 100 pixels across the surface of a planet. That's 100 years out. I mean, we're not going to build that right now, but the laws of physics don't prohibit us. So visiting it is a 1,000-year timescale, human effort, if even that, depending on how pessimistic you are. But studying it and knowing that evolution worked the same way is something we can imagine doing with bigger and better telescopes, not limited by the laws of physics. So we don't get to stand on it, but we get to know that we're not unique and that we're not alone, and understand evolution of life. Like right now, I cannot tell you how you go from chemicals to life, and anyone who says they can, not telling the truth. And you can't do that in a lab in a realistic way. If we look at and we find 10 Earths, that tells you that whatever that process is, though, it's pretty common. And in turn, that tells the chemists, oh, well, it must be this kind of process, not this other kind of process. So it'll illuminate the origin of life. It'll illuminate the formation of planets. That's kind of the end games. Let's see. I think there were some people who had their hands sooner. I want to try and be fair. Yes, middle chap.
Can you talk percentage of stars have solar systems, and what rate will we be able to sample with the Space Telescope?
From the Kepler mission, we would say that something like 50 to 100% of stars actually do have planets orbiting them. And the fuzziness is because there could be lots of planets Kepler couldn't see. A particularly important number is how many stars have planets that are close to Earth-sized, and we've all decided close to Earth-sized is between half the size of the Earth to 50% bigger than the Earth, and is in the Goldilocks zone, and there are huge arguments about where you put the edges of the Goldilocks zone. After those two arguments, you call that number eta sub-Earth, the number of Earths per star. When I was a graduate student, that number could have been 0. Well, not quite 0, because the Earth existed. When I was a postdoc, that number could have been anything from 0.001 to 1. Post-Kepler, we would say that number, the Kepler mission, not Kepler the scientist, we would say that number is somewhere between 10 to 50%. So 10 to 50% of stars have a planet that is Earth-sized in their Goldilocks zone. We don't know what they're made out of, because we haven't built the telescope that can measure them. They could be balls of rock, they could be micro-Neptunes, but that's about the number. So if we look at 100 stars, simulations say that HWO would find that the median guess is about 0.28. HWO would look at 100 stars and it would find 25 or 28 planets that are kind of the size of Earth in their habitable zones. So that's pretty good odds. Okay, further in the back, and then we'll come back to the front.
Of late, in the media, on the internet, there are lots of articles about Planet 9, like a small Neptune-sized planet.
In the edges of our solar system, yeah.
Right.
Yeah.
So would some of the techniques that you mentioned actually help in looking at it? It would be colder, but there is no star around it to obfuscate it. Would that actually? And what are your thoughts about those articles in general?
Yeah, I mean, if you're studying a planet, it's kind of cheating not to have a star next to it, in my opinion. But it would be more like the way we study Pluto right now. It's just a very faint planet. You need a big telescope to collect a lot of light. So it's not quite what I do. And then discovering it, the problem is, there are people who've done simulations that say there should be a 9th planet out there. They cannot narrow its position down very accurately. So you have to look at a huge amount of the sky with enough sensitivity to see a planet that's extremely far away. So you need a multi-gigapixel camera on an 8-meter telescope and survey the whole sky with enormous sensitivity. You might have heard earlier this year, we turned on a multi-gigapixel camera on an 8-meter telescope, the Vera Rubin Observatory, that's going to survey the whole sky. So if it's out there and visible from Chile, there's a decent chance that Rubin will find it. It might be too faint even with our 8 to 10 meters to do spectroscopy on. It's way the heck out there if it exists. Might have to wait for the 30 to 40 meters to actually get the spectrum of it. So, but it'd be cool if it existed. And not that, again, the lesson I sort of said is solar systems are very different than our own. We don't have any super Earths or mini Neptunes. It'd be nice if we did. So maybe it is our super Earth or mini Neptune. Yeah.
Could you comment about the locations of things? You talk about the Habitable World Telescope. Is that at the Lagrange?
Oh, that was, sorry, the earlier asked. The logical place to put it is at the Earth-Sun L2 point. So for the people who don't have their Lagrange points memorized, Sun, Earth, the L4 and L5 points are ahead or behind the Earth-Sun's orbit. What are Lagrange points? They're places where the Earth and the Sun's gravity balances so that your orbit is relatively stable. The popular one for telescopes these days is the L2 one. That's on the far side of the Earth from the Sun. It's popular because all the bright things, like the Earth and the Sun, are in the same direction, so you can block them with your sun shields. It's not perfectly stable, but it's pretty stable. It's getting a little crowded, but the stable area is about 1 million kilometers across, so we can afford to fit all the telescopes in there. So, and it's surprisingly easy to get to with rockets too. So.
And how would you point the telescope that uses the sun as
the one that uses the sun as a gravitational lens, you've got to know where your planet is before you launch it. You cannot steer that one around. So you say, oh, you've got a planet, here's the sun, I'm going to launch my eyepiece out in this direction. So you launch one per planet. And you even have to know where it is on Tuesday when you're observing it to get it accurately enough. But that's a hard one.
Could the speed at which the universe is expanding seriously limit observatory coming online 20 years down the road could provide?
Not really. In the universe, we think of it as expanding very fast, but the distances are so large that that expansion doesn't really move stuff further away. Like our galaxy, and all these stars I get to look at are in our galaxy, 100 light years away if we're lucky. Our galaxy is not expanding. Our galaxy is held together by gravity. Even nearby galaxies like Andromeda are not moving away from us. It's the galaxies that are hundreds of millions of light years are moving away from us, but they're moving away by 0.01 light years per year. So today they're 100 million light years away. When we launch the telescope, they'll be 100,000,010 light years away. That doesn't make a huge difference. There are proposals to measure that, which would be kind of cool, to actually measure the change in speed of the universe. But yeah, that one doesn't keep me up at nights as a problem, so to speak.
What's the farthest exoplanet we've discovered so far, and how far can we see with HWO?
The furthest ones away, the transit technique is actually pretty good for looking far away because it doesn't care about how big or small the system appears. It does care how bright the star is, but the Kepler telescope was a pretty big telescope. So the way Kepler looked at 100,000 stars is it picked one piece of the sky and just stared there. Most of the stars it could see, therefore, were about 1,000 to 2,000 light years away. I don't know if those hold the record, but that's kind of a cluster of the furthest ones that we know about. Habitable Worlds Observatory can't see anywhere near that far out. It would be sort of 100 light year kind of scales, and that's what limits us to this sample of 100 stars or so. And in turn, that's just set by the size of the mirror. If we doubled the size of the mirror, it could go 200 light years away. Really only depends on mirror size at this point. Probably approaching a good wrapping up point too, but people must be tired.
When you said clean, when you go out into space, do you have data of what space, how dirty space is, or how do you keep the lens clear? Besides meteors or comets, I mean, it's out in space.
Yeah.
Do you know what space?
We sort of thought we did. As I mentioned, the James Webb Space Telescope got smacked by a micrometeorite, tiny micrometeorite, much smaller than a grain of sand, although it had about as much energy, I want to say, as a baseball, just concentrated into a grain of sand. And that made a dent. And that was a surprise. And it only happened once, so maybe it isn't that grains of sand are common, maybe it just got unlucky. So Hab Worlds would be designed with a meteor shield around the mirror, and probably we would only point downwind, so to speak, that as the telescope orbits, it's moving through these micrometeorites that are spread through the solar system. You would point backwards so that the micrometeorites can't smack you on the front of your mirror. So it's definitely a concern list, and we're all looking apprehensively at James Webb to see if it gets another micrometeor impact like that. 1 per 2 years, and we do the downwind trick, and we have the meteor shield, means we would be okay for 10 years, but yeah, it's on the risk list, definitely.
There's not like debris that could cause a film on the lens.
That doesn't happen as much unless you bring it with you. So the gas from your rocket thrusters could condense back onto the lens, and that will, or the mirror. That in turn says don't use certain kinds of rocket thrusters preferentially. There's not really any gas in the solar system. The sun blows out just hydrogen gas that blows out from the sun, and that's pretty innocuous. So it's really the meteors that are on the risk list. That's one of several reasons, though, why L2 is great. Close to the Earth, there's a lot of gunk close to the Earth, so L2 is in principle safer as long as one of these micrometeorites don't come along and whack you on the side surprisingly hard. But I have friends whose job it is to stare at the shape of the James Webb mirror, and they're, every week when they make their measurements, they cross their fingers and hope there wasn't another one. So,
well, as I say,
yeah.
Let's thank Dr. McIntosh for a wonderful talk.
Good.